All right, we're looking at independent versus dependent probabilities. What's the difference? Well, that's what this first question is asking. What's the difference between independent and dependent? All right, well, I think our answer is B right here. Two events are independent when the occurrence of one event does not affect the probability of the occurrence of the other event. All right, two events are dependent when the occurrence of one event does affect the probability of the occurrence of the other event. So that's the difference between independent versus dependent. Independent, two events do not affect each other. Dependent, two events do affect each other. Okay, look at number 2 here. Here's a question that says, list an example of two events that are independent. All right, so here's 4 choices here. Let's look at our 4 choices. First, this A, not putting money in a parking meter and getting a parking ticket. Here's 2 events. Are these independent of each other? Well, I would say if you do not put money in a parking meter, your chances of getting a parking ticket are greatly increased. So these are dependent. What about this? B, selecting a queen from a standard deck, not replacing it, and then selecting a queen from the deck. That is dependent because if you don't replace it, you're going to affect the probability of this second one. What about C, a father having hazel eyes and a daughter having hazel eyes? Well, if the father has it, then that's going to affect the probability of the daughter having them. So these are dependent. Here's what's independent right here. Rolling a die twice. You roll it the first time and you get a 3. Then when you roll it the second time, you're just as likely to get a 3. Having a 3 the first time does not affect you getting a 3 the second time. So these are independent. All right, look at B here, or the B part. List an example of two events that are dependent. Okay, well, look at A. Drawing one card from a standard deck, not replacing it, and then selecting another. All right, this looks like it's dependent. Because if you draw a card and you don't replace it, that's going to affect what you get the next time because that card's not in there. So this is dependent. Look at B here. Selecting a ball numbered 1 through 12 from a bin, replacing it, and then selecting a second numbered ball from the bin. Once you replace it, everything's intact, and so you're just as likely to get what you did. It's not going to affect the second one. Look at C here, tossing a coin and getting a head, and then rolling a 6-sided die and obtaining a 6. When you toss this coin, it has nothing to do with rolling this 6-sided die, so these are independent. And then rolling a die twice, which we just had a second ago, this is also independent. So, yeah, this first one was the answer. All right, look at number 3 here. All right. For the given pair of events, classify the two events as independent or dependent. All right, getting caught in traffic, there's the first one. Spilling coffee in the car, there's the second one. These two events, are they independent or are they dependent? Does one affect the other? Well, I would say getting caught in traffic and spilling your coffee in your car are not going to affect each other. If you spill your coffee, that's not going to make you get caught in traffic. If you get caught in traffic, that's not going to affect you spilling your coffee. So these are independent. So looks like it's got to be one of these two right here that say independent. Okay. So are they independent because the occurrence of one affects the probability of the occurrence of the other? Or they're independent because the occurrence of one does not affect? I think it's C. They're independent. One does not affect the other. All right. Number 4 here. Determine these two events are independent or dependent. Returning a rented movie after the due date and receiving a late fee. Okay, if you return this movie late, you're probably going to get a late fee unless you know the person at the rental place, and and they let you off. So these are dependent because the outcome of returning a reading movie after the due date affects, so that's affects, the probability of the outcome of receiving a late fee, unless they just, let you slide. But still, it's dependent. All right, what about 5? A study found that people who suffer from obstructive sleep apnea are at increased risk of having heart disease. Identify the 2 events described in the study. All right, the 2 events, we're looking at sleep apnea and heart disease, so that would be A. We're not looking at a study in sleep apnea. We're not looking at a study in heart disease, having sleep apnea and not having it. No, we're looking at sleep apnea and heart disease. That's our 2 events. Now, are they independent or dependent? Okay, well, I would say what we're telling here is this affects the other one, so I would say these will be dependent. So, dependent. It says on here, they found that this one is at increased risk of having heart disease, so they're dependent. One affects the other. Number 6. Identify 2 events described in the study. Okay, this is a similar question here. So a study found that there's no relationship between being around alcohol abuse and developing cancer. So, right here, being around alcohol abuse and developing cancer. There's my 2 events. Okay, it says here there's no relationships. That means they're independent. So it's got to be one of these 2. Developing cancer is related to, no, this is not right. Being around alcohol abuse does not cause cancer, so the answer would be B. Okay, now let's go to number 8 here. Okay, you're flipping a 10-sided die that includes numbers 1 through 10, and you're spinning a 5-colored spinner that has equal chances of getting the colors blue, red, black, yellow, or green. There's your 5 colors. What's the probability that you roll a 3 and spin the color blue? All right, so we're going to do this right here. Probably getting a 3, and then you got the probability of getting a blue. Okay, probably getting a 3. There's only 1 3 on this die, and there's 10 sides, so that'd be a 1/10. Probability of getting blue, there's only 1 blue, and there's 5 colors. So I multiply these together. So when I do that, I get 1/50. Okay, are these dependent or independent? This one does not affect that one. That one does not affect this one. So these are independent. Okay, number 9 here. Okay, flipping coins, same thing here. Flipping a 10-sided die. All right, what's the probability that you roll a multiple of 4 and spin either the color red or green? All right, so we want multiple of 4, and then we want the probability of red or green. All right, multiple of 4, well, you got 4, 8, and that's it. 4 and 8 are the multiples of 4 and 1 through 10. All right, so there's 2 of those out of 10. There's my probability there. Now, red or green, well, there's red and there's green. There's 2 of those out of 5, because there's 5 colors. So I multiply those. All right, so that's going to be, when I multiply them, I think it's going to be 2 over 25. Okay, you just use your calculator. On mine, we're going to do 2 over 10, so 2 divided by 10 times, and then 2 divided by 5. All right, I get this right here, and I change it to a fraction, which is 2 over 25. So there you go, that was right. Okay. Now, I think these answers, there's answer choices on this, and they're in fractions. So if you do this computation, if you notice I got 0.08. Okay, what you can do is you take your answer choices, just do 2 divided by 25, and just do each one to see which one gives you this this decimal. All right, number 10. You're flipping a 10-sided die, the same thing here, okay? what's the probability that you roll a number greater than 5? So we want the probability that we get a greater than 5. And you spin a color that is not blue. Or if it's not blue, that means it could be red, black, yellow, or green. There's 4 of those. But we want not. Let me put it on there, not blue. All right, there's 4 of those out of 5. Now, probability of getting a number greater than 5, well, you have 6, you have 7, you have 8, you have 9, and you have 10. So there's 5 of those out of 10. Okay, so we multiply these. So when I multiply these, I'm going to get 2/5. Okay, I did the multiplication in my head, but that's what it comes out to. Number 11. You draw a card from standard deck of 52 cards. Oh, I didn't answer the second part on these questions real quick. Is this independent or dependent? Every one of these that we just did here are independent because flipping this 10-sided die and spinning this 5-colored spinner, they're not going to affect each other. So these are all independent. Okay, so now number 11. You draw a card from a standard deck of 52 cards. You then replace the card and draw a second card. What's the probability that you draw a 10 and then a 7? So you get probability that we get a 10 the first one, and then probability that we get a 7 for the second one. Okay, we're replacing the card. So since I replace it, that makes this independent. Okay, because when I replace that card, I still have the deck intact, and it's the first card I draw. It has nothing to do with the second card I draw. All right, so probability to get a 10. All right, there's 4 10s out of 52 cards. Probability to get a 7. Well, there's 4 7s out of 52 cards. So I multiply these together. Okay, so 4 divided by 52 times 4 divided by 52, and I get this right here. Let's change it to a fraction, 1 over 169. Okay, so this would be 1 over 169. All right, let's go to number 12 here. You draw a card from standard deck 52 cards. You then draw a second card without replacement. All right, that tells me right there this is dependent because we're not replacing it. Okay, so what I get the first time is going to affect what I get the second time because I'm not going to put that card back, which means what's probability you get a 10 and then a 7? So probability they get a 10 and then the probability they get a 7. All right, when I get this 10 for the first card, there's 4 10s and there's 52 cards. I'm not replacing it, which means when I go for my probability of 7, there's 4 of those, but now there's only 51. So I'd multiply these two right here. All right, so 4 divided by 52 times 4 divided by 51, I get this right here, 4 over 663. That's my answer. Okay, number 13. You draw a card from standard deck 52 cards. You then draw a second card without replacement. All right, if I'm not replacing it, that's dependent because it's going to affect that second card. What's probably you draw an 8 and then an 8. Okay, so I probably get an 8 for the first card, and then I probably get an 8 for the second card. Okay, well, this first card, there's 4 8s, and there's 52 total. Okay, now this second card, well, see, I'm not replacing it. All right, so that means now there's only 3 8s, and there's only 51 total cards. So I'd multiply those. Okay, so 4 divided by 52 times 3 divided by 51, that's 1 over 221. Okay, let's go to this one. You draw a card from a standard deck of 52 cards. You then replace the card, which means we're looking at independent here because we're replacing it, and now the deck is intact again. What's probably you draw an 8 and then an 8. So this is the same thing here as far as we want an 8 for the first card, then we want an 8 for the second card. All right, so this first 8, there's 4 of those out of 52 cards. But I'm replacing it, which means there's 4 8s out of 52 cards for the second one. So I would multiply those. Okay. So let's see here. I think we just did this a minute ago. Yeah. 1 over 169. Okay. What about this one here? You draw a card from standard deck 52 cards. You then replace the card and draw a second card. Okay, so this is independent now again because you're replacing it. So you're not, the first one's not going to affect the second one. What's the probability that you draw a number card and then a number card? All right, a number card would be 2. See, ace is really not considered a number card. Ace is not a number card. You got 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Then you have Jack, King, Queen. Those are not numbered cards. So here's number cards. There's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 number cards. Okay? 9 number cards. Get it all in there. You can see them. Well, there's 4 of these. There's 4 of those. 4, 4. There's 4 of each one of these, which means there's 36 altogether. 36 number cards. Okay? All right, so what we got here now, the probability that we get a number card for the first one, and then we want the probability that we get a number card again for the second one. All right, so on this one, there's 36 out of 52. Okay, now we're replacing the card, which means this second one's going to be 36 out of 52 also. So I multiply those up. All right, so this is independent because I'm replacing it. And so the first one's not going to have anything to do with the second one. Okay, so I type that in here, and I got this right here, 81 over 169. Okay, and there's my answer. All right, now this is the same thing here. You draw a number card and then a number card. So that's the same thing here, but you draw the second card without replacing the first card. So we're not replacing it, which means this is dependent. This is dependent because we're not replacing it, so it will affect the second one. So now, probability of a number card would be 36 out of 52, like we just did the previous problem. But if I'm not replacing it, now that means there's only 35 numbered cards and there's only 51 total. So I would multiply those. Okay, so, all right, I got it on here. It's 105 over 221. There you go. There's my probability. Okay. Now, let's look at this right here. Explain how the complement can be used to find the probability of getting at least one item of a particular type. The complement of getting at least one item. All right. Let's say we're doing this. Let me give you an example of this. Okay. You're going to pick, you're going to flip a coin 3 times. Okay. Let's look at what outcomes we could have. Well, we could have all heads. The first 2 could be head, and then the third one be a tail. Or this is now, these are all 3 heads. Now here we have 1 tail. Or we could have 1 tail this way, or we could have 1 tail this way. So all 3 of these right here involve getting 1 tail. Okay. All right, then we could get 2 tails. So we could have like these be tail and then this one be a head, or the head could be in the middle, or the head could be first. So these right here involve getting 2 tails. And then we could get 3 tails. Okay. So there's 8 different outcomes that we could get when we flip this coin 3 times. Okay. Now, we could do this. If I'm counting these, this is our counting techniques that we have talked about before. So this first one, I can get either a head or a tail. This second one, I could get either a head or a tail. This third one, again, I could get either a head or a tail. So if I multiply these, 2 times 2 is 4, times 2 would be 8, and there's 8 ways that you could do this. Of course, here they are. Here's all 8 of them. Okay? Now, what we're looking at in this problem right here is the complement. This says, explain how the complement can be used to find the probability of getting at least one item. All right, let's look at heads. Getting at least one heads. At least one. All right, when you say at least one, that means one or more. When you say at least one, that means one or more. Okay? So if you look at my outcomes down here, getting at least one head, which means one or more. Well, all these that are underlined have at least one head. This one here is the only one that does not have at least one head because they're all tails. All right, so the complement thing here is this. The probability that I get at least one head is 1 minus the probability that they're all tails, which means the probability that there's no heads. All tails and no heads are the same thing. That's the complement. So the probability that I get at least one head would be 1 minus the probability that I get all tails. Okay. All right, so which means on this one, the probability I get all tails or no heads, well, there's 1 out of 8. So this would be 1 minus 1/8, which would be 7/8. There's 7/8 probability of getting there's 7/8 probability of getting all at least one head. See, there's 1, 2, 3, 4, 5, 6, 7 out of 8. 7/8. All right, so answering this question, the complement of at least one, let's see here. Right here. The complement of at least one is none. So the probability of getting at least one item is equal to 1 minus the probability that you get none of the items. That's what we have here. See, the probability of getting at least one is the complement of getting none. See, all these versus this. So the at least one is the complement of none. Okay? Now we've got some questions here about that. All right, so number 18 here. The probability that a person does not get sick any day of the month in January is 0.126. The probability that a person does not get sick any day of the month. What's the probability that this person does get sick at least one day? All right, these are complements. These are complements here. When they do not get sick versus getting sick at least one day. These are complements of each other. So the probability of this would be 1 minus that. Okay, so it's going to be 0.874. There you go. Okay, now go 19 here. The probability that Central City goes a full week without a single incident of a truck getting stuck under the viaduct is 0.853. See, the viaduct down by, it's by Dairy Queen. Dairy Queen in Central City, the viaduct there's trucks that get stuck under that all the time. So the probability that you go a full week without a truck getting stuck is 0.853. What's the probability that Central City has at least one incident of a truck? All right, so these are complements. See, this goes a full week without a single incident. This is not having any. This is having none, which is the complement of at least one. These are complements. So the probability I'm looking for here is going to be 1 minus 0.853, which is going to be 0.147. Okay. Number 20. The probability that at least one bird poops on Jim's car while he's at work is this right here. What's the probability that there's no bird poops on Jim's car while he's at work? Okay. These are complements. At least one and none are complements of each other. So my probability for this question is going to be 1 minus 0.547, which is going to be 0.453. Okay, number 21. The probability that at least one person trips over the broken sidewalk today is 8.884. What's the probability that no person trips over the broken sidewalk today? All right, these are complements. At least one and none are complements of each other. So my probability is going to be 1 minus 0.884, which is going to be 0.116. We got 22 here. The probability that one or more people from Muhlenberg County wins the Fox Super 6 football challenge is right here, this right here. What's the probability that no person from Muhlenberg County wins the Fox Super 6 football? All right. One or more and no person, these are complements. One or more versus none, these are complements of each other. So my answer for this will be 1 minus 0.00326, which is going to be 0.99674. Okay, these are complements. All right, number 23 here. In a sample of 1,100 U.S. adults, 218 think that most celebrities are good role models. 2 United States adults are selected from this sample without replacement. Okay, so we've actually done this particular problem already, I think. We're going to do it again, though. Find the probability that both adults think most celebrities are good role models. Okay, so we're doing 2 adults selected from this sample. All right, so the first adult, there's 218 of those, 218 that think most celebrities are good role models. All right, so find the probability that both adults think most celebrities are good role models. So there's 218 of those out of 1,100. That's the first person. Now, once we pick this second person now, well, this person's already picked, so you're not going to replace him, which means for this next one, it's going to be 217 out of, well, this is going to be 1,099. Okay, let me get it on here where you can see it. Okay, so there's 218 out of 1,100, but once I pick that person, there's only 217 out of 1,099. All right, so now on this one, let me punch down 218 divided by 1,100 times 217 divided by 1099. And I get this right here, 0.0391. This is round to 3 decimal places, so I think I'm just going to leave it like this, 0.039. Okay. All right. I think I'm good on there. Let me check the answer. Yep, 0.039 is right. Okay. Now find the probability that neither adult thinks that most celebrities are good role models. All right, the probability that neither one does. All right. All right, so if I subtract then, since there's 218 that think they are good role models out of 1,100, if I subtract those two, 1,100 minus 218, I get this right here, 882. Okay, that means there's 882 that do not think that are good role models. So for this first person, 882 out of 1100. And then once I pick him, that means there's going to be 881 out of 1099. Okay. So 882 divided by 1100 times 881 divided by 1099. All right, I get this right here. 0.643. This 7 makes the 2 go up to a 3, so this would be 0.643. Okay. All right, so again, this first question, both adults think that they are. All right, this second one, neither one thinks they are, which means they both think they're not. So this is how many think they're not, and then once I pick him, that's how many think they're not. Okay, now part C, find the probability that at least, look here, at least one of the two adults, at least one, thinks most celebrities are good role models. At least one does. All right, that's going to be 1 minus the probability that they think they're not, which is what we have right here. See, this probability they think they're not's there, so I got to do 1 minus that. And that's what we were just doing on the previous problems. These are complements. These are complements. So I'm going to do 1 minus this, which is going to be 0.357. Okay? Those are complements of each other. All right, I think I got one last problem here, number 24. Okay. In a survey of U.S. adults with a sample size of 2,034, 315 said Roosevelt was the best president since World War II. Okay. Look here, 2 U.S. adults are selected at random from this sample without replacement. Without replacement, you can't put the person back. You pick this one and then you pick another one. So this is dependent. Find the probability that both adults say Franklin Roosevelt was the best president since World War II. All right. The probability that both adults say that they are. All right. So there's a piece of paper here I can write on. All right. So there's 315 out of 2,034 for this first adult, which means for the second one, there's going to be 314 out of 2,033. So multiply those together. Okay. So I'll do that real quick. 315. All right, I got this right here. Now, I think it says round 3 places, I believe. Yep, round 3 decimal places, as needed. Okay, so it's going to be 0.024. This 9 makes that 3 go up to 4, so 0.024. Okay. All right, now, part B. Find the probability that neither adult thinks that they are. So that means the probability that both think that they're not. So that means I got to do a little subtracting here again, just like we did the previous problem. Okay. So I got to do 2,034 subtract 315. Okay. So this is going to be a 9. That's going to be a 1. That's going to be a 7. 1719. Let me do it on the calculator, make sure. 2034 minus 315. 1719 is right. This is how many think that they're not. That Franklin Roosevelt was not the best president. See, this is how many thinks that he is. So if I subtract that, this is how many think that he's not. Okay. And in this problem here, find the probability that neither adult thinks that he's the best president. That means find the probability that they're both thinks that he's not. All right, which means I'm going to have this. Move this up some. 1719 out of 2034 for this first person. There's 2034. And then for the second person, 1718 over 2033. And I'm going to multiply them together. Okay? All right, so 1719 divided by 2034 times 1718 divided by 2033. And this is what I get right here. All right, so 0.714. This 1 does not make the 4 go up, so it stays. Okay, well, it's kind of hard to see this calculator on there, isn't it? So there'd be my probability, 0.714. Okay, and now this part C now. Find the probability that at least one of the two adults says Franklin Roosevelt was the best president. All right, at least one. This is the complement of this. Because this says neither one thinks he is. Both think that he's not. Here, at least one thinks he is. So these are complements of each other. So I'm going to do 1 minus this. 1 minus 0.714, which is going to give me 0.286. Okay. So this would be 0.286. Okay. Now, which of the events can be considered unusual? Well, I would say of all these right here, this one right here would be unusual right there because it's less than 5%. This one right here. See, this is not unusual. That's not unusual. That's not unusual because it's... so I would say the event in part A would be unusual because it's less than or equal to 0.05. Okay, so there we go. We got independent events and dependent events and the probabilities concerning those. So if you have any questions, just give me a holler. Have a good rest of the day.